Now we know that from our angular momentum analysis that these states they are orthogonal, right? So if I take the different value of L, then I get different, eigenspaces, or I get different multiplets, so they should be orthogonal. And if I take the same value of L, within that, different values of M should also be orthogonal, right? So this is our normalization, orthonormality. So condition. So we use this to find what the normalization constant is. So what is this in terms of, how does this equation look like in the position basis? So in the position basis, what is the measure? What is the space over which this integration has to be done? Can someone tell me? There is no R dependence, right? What is the measure here? So there has to be an integration over theta and an integration over phi. So there's a d theta and d phi. Can you fill out the rest of the, this is just the integration measure. So I want you to tell me what the limit, so, okay, we are in spherical polar coordinates. So what is the limit of theta? This
0 to pi.
Right. So this is 0 to pi. What is the limit of the azimuthal angle?
0 to 2 pi.
Right.
Sir, I still haven't got the logic of why we're taking the integration over R here.
We're not taking it over R.
Yes, I was wondering why.
Why we are not?
Yeah, why we are not.
Oh, because all the analysis of the angular momentum operator that we did before didn't have any R in it, right? So so the thing is that our total wave function will be a combination of this part and the R part. So they will be normalized individually, so that when we combine them, the combination would also be normalized. Right?
Oh, okay.
I mean, this doesn't have any R in it, right? I mean, you can take a constant R, but that's just going to complicate your life.
Oh, okay.
So, this measure is over a sphere, a unit sphere. So, which is in physics language, what is the measure? What is the angle over a unit sphere called?
4 pi.
Yeah, it has a name, right?
Steradians.
Yeah, so steradian, solid angle, yeah, all that fun stuff. Essentially, it's the area of a unit sphere. So that measure we need something else here. Can you tell me what that is? It's not just a integration over theta and phi. There's something else. What is the volume?
There should be a like a sine theta here.
Right. Okay, so this is basically what my volume measure is, right? So, and this, I can write this in a slightly different way. I can take this guy and write it as d cosine of theta, okay? Do you agree? But then I have a minus sign because the derivative of cosine theta is minus sine theta, right? And then the limit is from +1 because sine theta at theta equals to 0 is equal, if it gives you at theta 0 you get cosine theta is +1, right? And this limit going to give you in terms of cosine theta -1. And then this thing is just 0 to 2 pi. But because of this minus sign, you can invert the limit and you get d cosine of theta 0 to 2 pi d phi. Okay, so this is going to be our limit of integration, our measure. Okay, so L prime M prime Lm is going to be, if I if I introduce all the directions, if I integrate over all the directions, this is symbolically saying I'm integrating over all the directions. In other words, I'm integrating over the area of a unit sphere. Then I have here n hat Lm, and this is y L prime M prime star theta phi, and this thing is y L M theta phi, and this thing is what we just calculated, -1 to +1 d cosine of theta 0 to 2 pi d of phi. Okay, and this, we demand this to be equal to del L prime L del M prime M. Okay, sorry, is that clear?
Yes, sir.
Okay, so if I now do the normalization for YLL, then we get the equation where CL squared, the integration is from -1 to +1, d cosine of theta, the phi dependence drops out, and therefore the integration of that just gives you 2 pi, and then you get sine of theta to the power 2L, and that has to be equal to 1. Now, this is actually not an easy integral to do. So what is this integral? We have to integrate from -1 to +1 of d of cosine of theta times 1 minus cosine squared theta to the power L. And you can expand it in binomial, blah, blah, and but it's better if you just do a bit of change of variable. So let me just call cosine theta mu, and then this is 1 minus mu squared L. And then I introduce a new variable, and that new variable I'm calling it t, and t is related to mu by -1 over 2t. Okay, so if you do this, then this integral just becomes an integral from 0 to 1. There's a factor of 2 here, and there's dt, and then 2t, 2 minus 2t to the power L. Now, what we can do is that we can then identify this to be the beta function. So did you guys learn about the beta function in your math physics course or special functions course or any course? If you haven't, I suggest that you go and learn about beta.
So, yeah.
You know about the gamma function, right?
Yeah, we've done that in, I think, linear algebra theta correct.
Sorry, Rahul, you break. Okay, but beta function was not done. Who doesn't know about either gamma function or beta function here?
I know about gamma function, but not too familiar with beta function.
Okay, beta function is just defined to be a bunch of gamma functions. Okay, this is beta function. So do you know that the gamma function is the generalization of factorial? Are you aware of the relationship between gamma function and the factorial function?
N minus 1 factorial.
Yeah.
Gamma n. Yeah.
Yeah. Anyone else? I just want you to know about the gamma function. If it turns out that you guys don't have enough background, I will dedicate at least half a session or half a lecture on beta and gamma functions.
If I remember correctly, n minus 1 factorial, and then there was also this integral form, which I forgot. I'll have to look it up.
Well, you can look at that up, that's
yeah,
not important. Yeah. So do you know how the gamma function behaves on the negative, how to extend it to the negative part of the real number plane?
No, sir.
Okay. Do you know that? But you know that there is a there's a recursive relationship for gamma functions, right?
Yeah.
Yes, sir.
Which you can derive very easily from the fact that it's factorial, right? So if you use a recursive, if you analytically continue, you say, okay, I'm just going to assume that this recursive relationship is not just, so the idea is something like this, right? So, the factorial is, this, we have the real number line, and the factorial is valid for 0, 1, 2, 3, then 4, blah, blah, right? So, and then gamma of n is what? N minus 1 factorial, right? Or is it n plus?
I think it's n minus, yeah.
Yeah. So that means that the gamma function is, it's defined initially on these points, right? Or it's identified to the factorial. But then what you find is that you find an integral formula for the gamma function. And when you find the integral formula for the gamma function, it of course matches with all these factorial formula at these points, right? But it also gives you some values in between, right? So it extends the factorial function to the real line. So when n is what? N is 1. This is gamma of 1 is factorial 0, right? So, but gamma of 0 is actually a singular valued object. So the gamma function actually looks, if you plot the real gamma function, it's something like this, okay? Of course, this is going to grow very rapidly because it's just factorial. But the important thing is you have some sort of, some sort of integral expression for a gamma. But we also know that, very simple relationship is that factorial of n is equal to n times n minus 1 factorial, right? So what does this mean? This means that we have n times gamma of n is equal to gamma of n plus 1, right? Do you agree?
Yeah.
So that means that if you know this thing, you can extrapolate gamma to 1 before, right? By using, so now you see that if something miraculous happens, we know the value of gamma between 0 and 1. So by using, this, but of course it's not defined at 0, but there's a small price to pay. That means that we can use this formula to extend gamma to the negative part of the real line. Of course, because it's singular at 0, it will be singular at minus 1. And once you have extended it to the between 0 to minus 1, you can again use this to extend it from -1 to -2, and so on and so forth until -infinity. But of course, because it's singular at 0, it's going to be singular at all the negative integers, and it has something like this, okay? And you can calculate those using the integral formula, or not the integral, just recursive relationship, right? So the gamma function can be extended into the negative part of the real line, okay? Okay, this is just a kind of a, an aside. I wanted you to know this. It's a very beautiful, this is basically what beautiful mathematics is all about. You define something and you find it has a much larger, realm of applicability. The most beautiful application of this is the exponential, the Euler formula, right? Which brings together all kinds of different aspects of mathematics together. All right. So now what you do is that you use the fact that this is just a beta function. So this is a beta function, and you look it up in some table of integrals or whatever, and you find out what this normalization constant CL is, okay? And of course, in quantum mechanics, you can only define normalization up to a phase, and there is a like a convention for the CL, and that convention happens to be -1 to the power L, and it has to do with we will define the Legendre polynomial, and it's related to the 0th Legendre polynomials being positive. That's what this phase is about. So this is not very important for us. But this normalization constant becomes 2 to the power L divided by L factorial, and then square root of 2L plus 1, and then L, sorry, this is going to be, I think this is just 2L. Yeah, 2L factorial, and then divided by 4 pi, okay? So, I would like you to go and read about the beta function and derive this expression for yourself, right? Because that way you'll learn a little bit about the beta function, okay? And you don't have to, I think it's a good opportunity for you to learn about beta function. You don't have to be an expert on beta function, but somewhere down the line, when you meet the beta function or its cousins, then you will not be confused. Okay, so what we have found is that we have found this state, YLL, theta phi. So it's given by C of L, which is given over there, times e to the power I L phi, right? Sine theta to the power L. Okay, so this is. Now, once we have this state, is there a way to find all the other states, all the other wave functions without solving a differential equation?
Or-ring operator.
Yeah, so we basically now start applying L minus, on YLL, and up to some very important constants that I keep forgetting, that I have to look up all the time, we will get L minus 1, and so on and so forth. And this is not going to be a class on functions, special functions, but if you were to do it, then the expression for YLM is -1 L 2 to the power L factorial L, and then there's a normalization, 2L plus 1 L plus m factorial, L minus 1 factorial, 4 pi. This is a lot of very hard mathematics to derive these things, by the way. And we had to memorize all of this when we were students at Dhaka University for our quantum mechanics final, because we were examined for everything. Like, we had to memorize gazillion formulae. So sine of theta of m. You're lucky that I'm not making you do this. Okay, it's kind of pointless. That's why. This acting on sine theta to L. Okay, so this is basically the spherical harmonics in its full glory. Okay, so this is how you find it from one of the spherical harmonics. Okay, so one thing to note is that this is
Sir,
the
what's that L minus M? Like X, is that a product or?
oh no, yeah, it's a product. Yeah, sorry,
Oh,
it
okay.
should not be an X. It's a that acting on. Let me just say dot acting on this. Or yeah, let me okay, let me redo this. The product is, yeah, this times this whole thing. Okay? And we see that this is the phi dependence is here. And this is the theta dependence. So they factor. Okay. So